Hello everyone, this video is a short tutorial how to start STM32 application development under Linux. Actually there are a lot of free and commercial tools for development but the main problem is that it's based on some wizards and you have no full understanding how does it work and how to compile, flash and so on this application. So it's like Visual Studio, so you just starting it, pressing compile, drawing some files, and actually that's all. And this video is related how to do it from scratch without any commercial tools or free tools with IDE and so on, so it's from beginning. So let's start from toolset that you need to start development under Linux. So main tools is a compiler. For Linux there is no problem with compiler because you have GCC. Just one remark that it should be some special GCC, so it's of course it should be for ARM and it should be GCC which which provide application without no operation system, so this one. This software is very easy to install and can be downloaded from site. Yes, from here, so it's our toolchain, so we just download it's downloaded as archive, just extract it somewhere wherever you want. In my case it's extracted into OPT folder and that's everything. You can start to compile your application. It's not only compiler, it provides a bunch of tools. As you can see, it's this folder. Here it is, it's C compiler, C++ compiler, debugger and lot of other utilities for development. The next thing that you need is of course it's Flasher. The simplest way to start flashing your application is to download it from Segger site. It's some software which can be retrieved as Debian installer or some other kind of installer for Linux. It's easy to install and it will be extracted into OPT folder also. Mainly it's GUI tools and very easy, as I said, very easy to start with it. So for example, one utility is JFlashLite. It's simple GUI flasher. Here it is, so it say which microcontroller, micro MCU you have connected, its interface why it has connected and the speed of this interface. So let's start it, and it's, as I told, it's GUI application and it's very simple to do with it. Let's show our board. So it's our board and we can, for example, erase the chip. So it started erasing, now it's done. As you can see, the green LED stops blinking, so it means that the flash is erased. To check out our hardware, we can flash some test application. The link will be below the video, so I will open this application. Let's test application and let's start flashing it. It's flashed and now let's press reset to start our application. As you can see now, it's flashed. It's blinking again. It's just flash. But it also provides some another tools, more complicated tools. It's like debugger, RTT viewer, and so on. You can see it's installed here, and that's all application. It's Qt based application. It's huge set of it. You can refer to the documentation regarding these tools on his official site. There are a lot of documentation related to these tools. But the main tools under Linux for flashing, debugging, it's OpenOCD software, which can be downloaded from here, from this official site, or can be installed using some package. So also very easy to install. The documentation how to start with all this tool set, there are on our GitHub page. It's quick start guide section, how to install toolset. So as I said, it's our compilers, just download, extract it, it's install our OpenOCD. Of course, for development you should have some build system. In our case it's Make. It's very simple, but if you need you can use CMake, it doesn't matter. And DDD is GUI front end, our GDB tools, it's debugger. So, and installing the toolset from Segger. So it's downloading that packet and install this packet. There is one problem with Segger toolset, maybe just under Linux Mint. I do not didn't deep investigate this situation, so there is no library path provided for this utilities. As you saw, this is Qt based application, and there is some dynamic libraries for it, but after installation there is no path for this library, so this path should be added into this. It can be added just like export LD library path and pass to your toolset where these libraries are located, and there is also recipe how to persist this path. Okay, maybe let's start from our hardware. To develop STM32 you need some hardware, and main thing it's our JTAG emulator for it. So it can be purchased from AliExpress. As you can see, it's very cheap board. The next tool is some evaluation board on this MCU, so it's this one. It's also very cheap, and it's very easy to purchase it. The documentation for this board can be retrieved here from its blue pill board. So there's a bunch of documentation, schematics, some suggestion how to start with this board, and so on. So let's start with, maybe let's show what we have connected. I think you already saw it. So it's our emulator connected, as you see on the AliExpress site, and our evaluation board is also connected here. So just two things that you need from hardware point of view. Okay, let's download our project template to see how it's work. So it's cloning our repository, which contains a template of our project. And after that, let's start to see what we have in these folders. So we downloaded this software, and what we have in this folder, of course, it's makefile. It's STM32 peripheral library. It's a library provided by STM, and it covers all functionality with hardware abstraction layer. So it's very easy to set up some GPU, UART, and so on. Everything is prepared in there. The next folder is source folder. It's like some short demo with some debug extension development by me. It's Segger RTT. Segger RTT is some toolset for runtime tracing. It's not only tracing, it's like all console, so it's a bidirectional communication between our evaluation board and our PC used for development. For communication, it's using JTAG, so you don't need to invent any serial communication or something like this, any additional wires, any additional hardware bridges. So it's very simple to start with it. The next folder is OpenLCD. It's just some configuration for OpenLCD to flash it and start debugging process. Next folder is linker. That's linker script for it. I will talk more detailed later about it. It's FreeRTOS. FreeRTOS, it's a real-time operation system. It's very good operation system. It has a very small footprint in RAM, in flash. It has very efficient scheduler, and it's very easy to use. It's well documented. The next folder is documentation. You can walk through all this documentation to have better understanding about the programming of this chip. And it's config folder where all configs are put together to simpler configuration of this project. So it's FreeRTOS configuration, it's tracer configuration, and it's configuration of our chip. So okay, let's open it in some editor. Here it is. So more detailed about makefile. So makefile is the path to our installed toolchain. If you have choose it another folder to install it, so please change this path. After that we have project name, but it's not very matter, it can be as it is. So it's a list of our sources. If you add some sources into this template, you should add it there. Also, important section is include a path. If you provide some additional folder with header files, you should add them here. And all another stuff, I think, are set up, but if you need, you can investigate it more deeply. Okay, the next folder is STM32 peripherals. So it consists of a standard peripheral library provided from STM. It consists of core files, it's Cortex M3 cores, it's header and source files, and also some assembler startup file, which provides some basic startup script, not script, C code for starting the software. And the next is C file for setup in clock frequency on our target board. All configuration, as I told, I put it here. So it's include all stuff that we need. It's for debug configuration. It's also add full assert functionality. Full assert functionality is some additional printing in case when you toggle in STM32 peripheral library with wrong input parameters. Segger RTT, it's, as I told, it's very simple utility. How does it work? You just put in some your traces into memory. After that it can be retrieved by using JTAG and represent it in the human readable way. Open OCD scripts. Let's start to link your script. In order to adapt this project to another MCU which mainly has different size of flash and RAM, it's enough just to edit these sizes. All another stuffs are calculated automatically based on this data. As I told, FreeRTOS it's also very simple from the source point of view. Just as you see, it's just few files. It's included for it. And the documentation folder, as I told, that's I think everything. Okay, let's start to do some stuff with other application. So it's make basic application. And you can see all available options with, which you can do with it. Okay, so let's maybe erase our software. Yes, we did it. As you can see, it stopped blinking, so it's erased. Okay, let's start build our template. It takes some time to recompile all sources because there are a lot of components of it. It's done. At the final stage you can see some additional data about our flash. The main things is text. It's area where our execution code is located, its size, and also we have data and BSS section. Actually these two, its RAM size should be suitable for RAM size. If it's not suitable, of course you can compile it, and there will be some warnings about it. And you can flash it. As you can see, it's already flashed. For the build there is two type of builds, so we did build for debugging, but we can do release build. As you can see, the sizes are different because different optimization and some debugging components are thrown away in that case. For example, real-time functionality or real-time console is thrown away, so it's now, as you see, it's about 10 kilobytes in flash. Before it was 38 kilobyte in flash, so it's already optimized. Let's flash it again. So it's also working version. Let's build the back version again to see some additional functionality. Actually, the build process of everything is started just first time. If you build it again, it's very fast because there is nothing to do with it. There is no changes in sources. So maybe let's start some debugging session. So we have started data display debugger window, and let's press add some breakpoint here. Start, it's here, and maybe we add some additional breakpoint into our task to figure out what's going on. We have, for demonstration, we have started just two tasks. Starting schedule is actually this task is just blinking off LED. Here to continue our ride. As usual, of course, you can see the variables. The let is on, but if we continue execution, now it's off, value is false, on, off, and so on. So it's fully functional in debugger with GUI and so on. You can read a lot of documentation about the GDB. It's very useful tools, and there are a lot of functionality relative to it. Okay, stopping debugging session. And the next thing which is integrated into our template is debugging console. It's a console from Segger. Maybe let's clear and start software again. So it's printing some initial prints about main start, our starting of our task. All this information are available in our main function. Here it is, main start. After that, tasks are created and scheduler is started. Task 1 start and task 2 start. It supports different debugging level. If you can see, it's log debug, but another print is under log info. Okay, let's start to turn them on. Sorry. It provides some information about what we can do with this console, so it's set some tracing level currently and print the operation system statistics. More detailed information can be retrieved by this way. So trace, and it's set some tracing level. Let's start from trace show. So currently we have level log debug. So for example, lock info shouldn't be showed in that case, just debug messages and more important messages like warning, error, critical and so on. Let's change this level to see the information from our task. In our code you can see each blinking we have some prints in info level. And you can see these prints here. You can stop the sprints by setting debugging back. Okay, it's stopped. But it's also the problem of this tools underline of this. You can see some bottom lines are cutted, so actually you can see some prints. Trace help. It's available from here, but well, let's just clear terminal. So it was trace relative things, and another things it's some statistic relative to running FreeRTOS on our MCU. Start command, and you can see the current state of our operation system. You can see 3 tasks with their IDs, so it's idle task, it's task 1 and task 2. You can see it on the sources. Here it is. Task 1, task 2, second. So it's the state of this task. It can be running, blocked, especially this print are provided from idle tasks, so all another tasks will be blocked in this time. It's a original priority of our task, and it's an inherited priority. This actually in real systems this value can be different due to locking some section by and waiting them by some more priority task. That's a time spending on each task. This is a stack value for each task. And this is a percentage representation of this time. Also you can see the total running time of our system. Also there is available information about operation system heap state. It available heap size. sorry, consumpted heap size. So it's total value and its maximum value. Can do it again. If you can see, the running time is increased. All the other values are more or less the same. Just few words about our templates. It supports some additional functionality. It controls stack overflow. It's very important for embedded system because the memory size is limited. And if the stack will be is overflowed, you will see some prints relative to this in our console. It's assert filet. For example, you call some STM functionality with wrong parameters, you will see this print. This is a functionality relative to our system clock filet. For example, it's due to soldering an external oscillator or something like this. Also we'll see the print. And also it's hard fault handler. It's some, for example, accessing memory which is memory range which is not valid on our board. You will see this printing. Actually, that's all. Thanks for watching.